Really delighted to be here today. My name's Lucas. I'm a researcher at the Oxford Smith School. In my research, I seek to explore and resolve data gaps in the very fundamental data, which is far upstream in the sustainable finance value chain. And I tend to do this with machine learning. So in this paper, we're starting to tackle the availability of solar PV installation data around the world. This started at a big Earth hackathon in Stanford in April 2018. And we secured the support of Descartes Labs, who's a spin-out from NASA, and they're building a giant cloud computation infrastructure that allowed us to do this work. So why is solar PV important? Well, we have estimates from the IEA that we need a sort of a 10,000-fold increase in the deployment of solar PV. So this is a major driver of transition risk, and it's important both to get sort of the sustainable development story and the decarbonization story right at the same time. There's no global asset level data set of solar PV generating stations, especially one that's complete with installation dates. So if we're trying to understand the real drivers of solar PV diffusion, this becomes difficult. We might have good data in some geographies, but certainly not most. And so this problem is particularly acute in developing countries. Asset level data, so we need to understand the inherently spatial energy system, and we're trying ultimately to facilitate a transition to a 100% renewable energy system. And so for renewables, which share sort of the inherent complexity of the environment, in that their generation is from the wind and the sun, which means that we need sort of data streams which are able to reduce the complexity of the natural environment to understand their intermittency and ultimately get to a 100% renewable system. And so a little bit of public good in understanding asset level data tends to go a long way, and it allows us to propagate those risks from the real economy up to the financial economy. So as a preliminary analysis, how did we think we were going to do this? We started just with this question of whether it would be possible with remote sensing imagery to even detect solar PV in remote sensing imagery. So we did a quick sort of pixel-based spectral unmixing in some areas in California, and we found that sure enough, we could detect solar PV, and so we thought there was something, it was worth taking a few extra steps to see how far we could go to actually come up with a much fuller data set. So this is just showing some unsupervised classification. But we thought, okay, I think there's something here. We're going to do a semantic segmentation exercise, which is basically a pixel-based mapping. So for one pixel, some square meter area of the planet's surface, map that to a classification of either yes, there's solar there, or no. So there's a simple binary classifier, and we use a convolutional neural net to do this. This is sort of the leading AI method now. We had some intuition about why this might be possible. So PV panels, in their very nature, are designed to absorb light across sort of a wide range of spectra. And so we were going to use this sort of natural property of what PV panels do to detect them, which means that we thought that perhaps even superhuman performance might be possible because these sensors are receiving data in spectra that are outside of just sort of the normal red, green, blue human vision bands, but also into sort of ultraviolet and infrared. So this was sort of our intuition. And we wanted to combine this with some efforts to control for clouds, some seasonality, some atmospheric conditions. And so we thought, okay, actually there's two main data streams that we could harness to try to detect solar PV. So we started with some training data. This training data came from a public source. It's OpenStreetMaps. We scraped all the solar PV installations off of OpenStreetMaps and filtered them just for a minimum area. We decided to look for utility scale solar PV. That was the resolution of the imagery that we had. And we created a cross-validation set. And then also, as we were going along, we had to bootstrap some more data. These are the sensors themselves. We have two satellite constellations. One is Spot 6-7, and so this has a maximum resolution of 1.5 meters. And the other is Sentinel-2. This is a European Space Agency constellation, which has a wide range of bands with a maximum resolution of 10 meters. So oftentimes it's not something that you would look at and say, there's solar, like you would in like a Google base map, for example. But because of these extra bands, we thought that it's something that an AI system might be able to figure out. For the corpuses, we have, for Spot 6-7, we have sort of a single global mosaic from some point in the last kind of 4 years. And for Sentinel-2, we get a new image every couple of days. So this allows us to look through the back catalog and determine when these things were actually installed. So this adds this very fundamental property that allows us to interrogate the diffusion questions a little bit better. So this is our machine learning pipeline. I won't go into too much detail on the machine learning stuff, but if people do want to talk to me about that or have questions, I'm very happy to field them. But I will describe the pipeline a little bit. So the pipeline features 3 different computer vision systems and 2 sequence models. So sequence models are the kind of models that sort of take a time series as an input and then create some output. Computer vision models are the types of models that take sort of an image and then put some output. And I've shown here we have sort of a population mask to begin. We do some other stuff around masking for vegetation and water. And then then once we're fairly confident with a detection, we go through the entire back catalog of imagery to try to determine when it was installed. And then the last thing we do is we verify the installations by hand. So we did take the time to go through the entire data set and generate samples for everything that we looked at and verify that, yes, we had indeed correctly identified a solar PV installation. So this is some of the models, but I think I will just skip straight through those. So the deployment area came out to about half of the entire land surface area of the planet. We did this because we wanted to, we didn't want to be searching in like northern Canada or the middle of the desert where we were quite certain that solar wasn't likely to be. But we did test this hypothesis. We took our cross-validation set and we looked at where it was relative to human population, and we did a dilation of the area that is covered by human population and found that with about 7 kilometers from any given human population, that seems to be the extent that people are willing to install solar PV. So we at least tested that hypothesis before we went and did our deployment. So in this image here, it might be a bit difficult with the resolution, but the red shows all the holes where we didn't search for solar PV, and then the green outline shows where we did search. So in total, that's about 72 million square kilometers, which is about almost half of the planet's land surface area. So some results. We trained our main computer vision models. Took about 36 hours on a suite of 4 GPUs. The deployment took over a human lifetime in CPU time, and also about 2 years of GPU time. And we went through about 550 terabytes of imagery. And the result of that was 68,000 solar PV polygons, which came out to about 209 gigawatts of installed capacity. For about 57% of those polygons, we were able to determine the installation date, and that covers detections in 131 countries, 42 of which were not previously known in any public data set of PV installations that we had. So you can see here sort of the growth, the time series of growth of PV, and sort of the cumulative and by country amounts of PV that we were able to detect. What does this look like in terms of actual images? So on the left, you have the input images in RGB. So these are the 3 spectra that we see in visible light. And then I've shown the prediction maps from the 2 satellite constellations. And then finally, the vectorization, which we use to generate a footprint. How we determine the installation capacity of each installation. We hypothesize that there's a linear relationship between the area of a solar PV installation and its actual generating capacity. And then we went and tested this, and I'll show you that regression in a second. We had some false positives, of course, that we had to go through. So the models seem to really like sports fields. Something about this sort of green. Something about I think the green sort of the green wavelength tends to be one that the model was picking up a lot. Some shape factors, so these ones with greenhouses and chicken coops, it tend to pick up a lot of. Actually, I thought we picked up so many chicken coops and greenhouses and cattle sheds as well. I thought, okay, our next job will be to map the world's agriculture infrastructure. Other high aerosol areas, it seemed to really pick up the UV absorption quite a lot. So aerosol areas over deserts and sort of low density urban areas, it picked up quite a bit as well. I should mention actually, we reached the end of the cloud on this deployment. People say the cloud is infinite, but we actually reached the end of the cloud. We were trying to spin up more GPUs, and Google told us that they had no more GPUs to give us. And so we were held up for 3 days while Google went and physically installed more GPUs for us to continue our deployment. So area versus megawatt capacity, pretty simple linear regression. This is from some data where we sort of hand drew the outlines around the installations for installations where we knew what the megawatt capacity was. And this is a time lapse of our detections, which I've just sort of broken into quarters, so it's manageable. Light blue shows sort of the more recent installations, and pink is sort of the earlier installations. It's a little bit difficult to see here, so I've broken it out into some regions as well. So you can see the EU28 having sort of very well established presence of solar, but rapid expansion of solar PV in China, in sort of different regions of the United States, India, and some countries in the EU28, which sort of surprised me. There's a handful of holes in here, which are kind of auspicious, like in Austria. For Netherlands, seems to be somewhat late to the game. Installations of PV really pick up sort of through our time window in the Netherlands. And then just over the period, we see quite a lot of PV emerge. So it'll be difficult to see on here, but we wanted to explore, with this data set, it's highly localized, so we wanted to understand the diffusion of solar PV in sort of a highly localized spatial way. So we came up with some spatial covariates that we thought were important and might sort of point to fundamental, some of the fundamental drivers of solar PV diffusion. So we looked at solar irradiance, GDP, and population as sort of fundamental sort of spatial elements that might be correlated with the diffusion of PV. And then we tested these with a handful of kernel filters. So we use these kernel filters to be able to bring in spatial elements that were a little bit further away. So that allowed us to test hypotheses like, okay, well, maybe we have a not in my backyard sort of syndrome for solar PV. So people want to install solar PV, or companies or governments want to install PV, but they don't want it in immediate proximity to populations. So by bringing in sort of by using these Gaussian filters, we're able to bring in we're able to test how the distance away from population centers or GDP centers or changes in solar irradiance affect the deployment of PV. So this might be a little bit difficult to see, but we can plot that against radius, essentially, from every installation. So these are betas, these are coefficients for irradiance, GDP, and population by country. And you can see they exhibit quite a spread. So in China, for example, we find that across all radii, solar PV installations are inversely correlated with solar irradiance. So solar irradiance has not been a particularly deciding factor in the siting decisions for PV in China. But we find at small radiuses, radii, things like irradiance, population, and GDP are material in other countries. This last figure here on the right shows the radial density. So this is a measure of autocorrelation in the data, spatial autocorrelation. So where we see higher radial density, it means that solar PV installations are more clustered. So it means that there is some mechanism that is bringing those installations closer together, even when we divide them out into different countries. So we see the most clustered installations in the United States, in China, and in India, and that happens across different scales. So you can see China, the line that at the top, sort of happens on sort of more regional scales. The x-axis goes out to 500 kilometers, in case you can't see that. So autocorrelation is actually, in fact, strongest in the window of sort of 200 to 500 kilometers. Whereas in the United States, you can see that it's strongest in the window of sort of 0 to 100 kilometers. So this indicates that it's sort of at the state level and sub-state level. And so we use autocorrelation to sort of to control against our covariates and say, well, our covariates explain siting, PV siting decisions only so much, but we see that there's this other autocorrelation, and so we need to explore other mechanisms that sort of illuminate further those siting decisions. So our conclusions, this is the first time the entire planet has been searched for individual capital assets, to best of our knowledge. We're publishing this data set publicly with the World Resource Institute global power plant database, so this will be available to everyone to use. And we find sort of in our analysis of covariates and autocorrelation, we find that the siting decisions of PV are sensitive to covariates across sort of meaningful scales, so scales that have to do with sort of the proximity of cities and towns and state borders and national borders, but they're also highly autocorrelated. So we need to better models to unpack what the mechanisms might be. And we're publishing this data set to sort of unleash the creativity of whoever wants to do some of that analysis. And we do see that trends vary meaningfully at the nation-state level as well. So in our covariate analysis, not across different countries, they don't all look the same, and that means that there are things that are happening at the nation-state level to determine how solar is sited and diffused as well. Thank you very much.